Welcome everyone. Welcome to the webinar today. My name is Gary Yan. I'm a senior application engineer in RISA. So today we're going to be talking about some basics of the dynamic analysis in RISA-3D. So before we get started, if you're using Zoom, you can join in using your phone call or using the computer audio. And if you have any question during the presentation, you can go ahead and click the Q&A button on the bottom of the Zoom screen, and then you can type in your question in the chat box. So my colleague Ben or someone else would be able to answer your question during the presentation. Now in today's presentation, here is an overview of the presentation. I wanted to first talk about some dynamic basic knowledge in terms of what is the equation for motions, period, frequency, mode shape. And also I wanted to talk a little bit about how to perform a response spectrum analysis and a time history analysis. Those are some basics of dynamics that I would like to refresh your memory for your dynamic classes in college. I'm not here trying to teach you dynamics because it's a very limited time. So I just wanted to refresh your memory so you can catch up the parts that when I do my demo, you will know what I'm talking about. And the second part of the presentation, I will do a quick demo using 3 different models. The models I selected are representative for each of the analysis we're going to perform today. Namely the Eigen solution, which is to obtain the period and frequencies and mode shapes. And the second one is a response spectrum analysis, RSA. And then the third, I will show you an example of a time history analysis. So for part 1, dynamic basics, I wanted to start with talking about what is period. So most of you are pretty familiar with this picture here. We have a mass and a spring attached to it. So if you pull the mass away from its initial position, it's going to oscillate near its neutral position. So if you draw a plot with the displacement over time, you got these sine or cosine curve. So the period is defined as the time it takes to complete one circle of oscillation, meaning the time between 2 nearest peaks. Now for equations of motions, most of you may be more familiar with this photo. This one is very popular in most of the dynamic books. So we have a mass here and a spring attached to it, and we have a damper. And we have a excitation here, Ft, and the equations of motions is described in this equation. So on the left-hand side, we have m times x double dots, stands for the acceleration. So you use a mass times your acceleration. This will be your force of inertia. Plus the c times x dot, this is the velocity times your damping factor, which is to get the damping force. Plus your k times your displacement, that's essentially your internal forces coming from the stiffness of the system, is equal to your excitation here, F. Now for a single degree of freedom system with no damping, this equation can be simplified as below. So with no external forces, your right-hand side will be 0, and the left-hand side will be m times your acceleration plus k times your displacement equal to 0. So this is a second order differential equation. If you want to solve it, you can assume x is a sine function or a cosine function. So if we're using sine function over here, plug this value into the equation, we can cancel out the phi sine omega t, and we can get omega is equal to square root of k over m. Now, based on the definition of the period for sine curve, the t is equal to 2 pi divided by omega is equal to 2 pi square root of m over k. So this equation is simply the general form of calculating a period for a single degree of freedom system and the free vibration. If we move to a multiple degree of freedom system, now the format of the equation is very similar. as you can see. But instead of a single value of mass, we have a mass matrix and also a K matrix, which is a stiffness matrix in here. So I'm not going to jump into the mathematical manipulation here, but if you use a similar procedure, you can solve this equation. The determinant of this matrix is equal to 0. So by solving that, you can get a few omega values. So the number of omega values is depending on how many degrees of freedom you've got. So in this case, we have 3 degree of freedom system. So the I is equal to 3. So we will get 3 omega values. These are also called eigenvalues. And also we have 3 phi values, which is 3 different eigenvectors. And each vector is representing a single mode shape. So as you can see, for mode 1, mode 2, mode 3, we have different mode shapes. So the phi is basically a representative of these shape. So in RISA-3D, we can perform the model analysis to get the period and the natural frequency of the structure once you model it. So in RISA, we actually have 3 different dynamic solvers to obtain that. So we have the standard solver, which has been there for many years, and it has been proved to be very efficient and very accurate in getting the period and frequency of the system. While now the most popular or advanced one we recommend the user to use is the advanced solver. In the advanced solver, we were using actually 3 different type of solvers, and we're going to take the most efficient one out of these 3 and use that solver in the analysis. So this one is always recommended. And then we have the third one, which is called a RISA-vector solver. So this solver is using a different approach. It's a load dependent. Basically, you apply a vector to the system and then you get a approximate eigenvalues and then period and frequency of the system. So for this RISA-vector solution or RISA-vector solver, it's an approximate solution. So it has its advantages, which is if you're doing an RSA, you can use fewer modes to get a more mass participation. And also it's saving you a lot of solution time and it requires less memory. But the disadvantage of it is it's not actually solving the equation that I mentioned, the mx plus kx equal to 0, that equation. So it's not actually giving you the true eigenvalue or the true period of frequency of the system. So if the main goal of your analysis is to get an accurate period or frequency, that's your main goal, then RISA-vector solver is not recommended in that case. Now, moving to the response spectrum analysis. So a response spectrum is essentially a spectrum that describes what is your response for a single degree of freedom with a particular period. So if you look at this chart, we have the vertical axis, which is describing an SA, which is a maximum response in terms of gravity acceleration. And then the horizontal axis is a period of the system. So if you plug in a period of the structure, you can get a response. So that's basically what the spectrum is. So for different earthquake, you can imagine you will have different spectrum for each earthquake. Develop this spectrum. So here we have a seismic excitation here. So we're going to apply this seismic excitation to this single degree of freedom system. So here we have a t equal to 0.5 seconds, let's say. And then we get a response for this system. And then we will capture the maximum response of this system. And then we have these 2 values, t is equal to 0.5 and a maximum response. So using these 2 values, we got 1 point on the spectrum. And then we can perform these multiple times for different period and get different responses. And then we can plot the whole spectrum over here. So as you can see here, the steps that we do to apply seismic load to this single degree of freedom system is actually a time history analysis, which I will be talking about later on in this presentation. So most of the code, they will use a collection of different earthquake records that's been captured before in history and then came up with a kind of a roughly upper bound for those responses and then use it for your design. If we look closely of this spectrum, this is taken from actually the ASC7. On the very left-hand side, we have a period that's very, very small, which represent a pretty rigid structure connected to the ground. And on the right-hand side, we have a very large period, which represented the very soft structure connected to the ground. I like this photo very much because it's very representative of the case here. So in these two cases, on this case here, as you can imagine, the relative displacement between the structure and the ground is not that big because it's very rigid. And on this end over here, you can see that since it's so soft, it's like it's isolated. The upper structure wasn't actually affected by the seismic or the excitation much. And between these two periods, you've got a peak here, which represent the structure period, which is close to the major period of the excitation. So you have a resonance happens. So I think the most famous case for the resonance is a Tacoma Bridge. I think most of you may have watched this video before. Even though this wasn't excited by the seismic load, it's by the wind load, but it pretty much represents how big the amplitude of the response can be if you have a resonance. Sorry. Now in RISA, we have different spectrum that you can select from the library, and then you can also create your own spectrum if you want. It's pretty easy. I'm going to show this also in the later on the demo here. So how to utilize the response spectrum to perform your seismic analysis? So ASC7 gives like two methods you can use it. The first one is very popular, is equivalent lateral force method, ELF. So in this method, we assume there is a dominant period for your system, and then we use that period to calculate your response. We plug in that period. That would be the single period to represent the whole structure, and then we get a single response. And using that response in acceleration, we use that times your mass, and we divide it by the R times IE. So the R factor is here to bring you to actually reduce your responses. The reason for that is this spectrum is developed for a elastic system. But in reality, in your structure, you have yielding, you have a cracking, so you have ductility in there. So the actual response is not going to be as big as what's shown in this spectrum. So you needed to divide it by this R to bring it back down to a ductile system response. So that's basically what R is for. So in this way, you can get your base year. Another way is to use a response spectrum analysis. In this case, you would have performed these steps for multiple different mode shapes. So as you can see here, you have different period for different modes, and then you will plug into this plot and get different SA factor, which is your response for different modes. And then considering your mass participation as well as your mode shape, you're going to get a force distribution for each of the modes. And then using a certain way, you can combine those different force distributions to get a total response of the system. So as you can see that this one captures the mode shape in different modes. So if you have a system that don't really have a dominant mode shape, the RSA is actually a much better choice. And I think in some cases, it is something you have to do for your analysis. So for combining those mode shape results, there are like multiple ways. I think most of you have we have the typical square root of sum of the squares, or we have the complete quadratic combination. So this one, I think it was used a long time ago, and I think it's a basic method, and I think very few people are still using it. And these two are more advanced method. They all have their own advantages. For instance, the CQC can account for some closely spaced modes because it has this kind of a weight factor in there. So depending on what type of structure you are doing, so the engineer has to make decision on what method they're going to use for their RSA. Now, the third part I want to talk about is the time history analysis. Excuse me. So time history analysis, as I mentioned in the previous one, when we developed the response spectrum, you simply apply a seismic excitations. It's like these excitations over time, and then you apply it to your system directly to get the response of it. So this is a more direct method compared to RSA, which is, you plug in the period and you get your response. So these time history analysis not only can be used in seismic, it can also be used in analyzing equipment vibration or some blast load per se. So basically, we still have the equations of motions here. The same equation will be used, and we have this excitation here. So as you can see, that excitation is changing over time, so you can't solve it directly. So what you do is to divide this time history analysis, divide this excitation into small little steps. So each step can be considered as linearly increased or decreased. So for solving each step, we will plug in the forces of that particular step into this equation and get the response of this whole system for that step. And then the result of this step will be used as the initial condition for the next step. So we're going to solve it like step by step, and then we can get the total response for this system, for this particular seismic load. Now, for solving the time history analysis, we have the direct integration method, which I think it was very widely used. So you basically solve the dynamic equilibrium equations like directly by doing it in like a numerical integrated solution on each single step. And we are using the HHT, the Hilbert, Hughes, and Taylor integration scheme. So this scheme is actually a more advanced or more, I would say, a more updated method compared to the classic Newmark method. So this method has been proved to be relatively stable and very accurate in solving time history analysis. And it has its pros and cons. The pros is it doesn't rely on any model analysis because it's directly solving the equation. And you can change the damping because it's, each single step is solved separately. So you can use various damping ratios. And the cons of these is pretty obvious. If you solve it in each step, you're going to take a lot of time to solve it. And so the time step that you're going to define is very important. So the steps that we recommended is typically 1/20th of the excitation period, if it is like, for example, a excitation from the equipment vibration, or is like 1/10 of the smallest natural period if it is like something like a seismic load. Now, for the model, the superposition method, this is the second method we can do for the time history. So this method is rather complicated. I don't have time to jump into these details of the equations here, but it's essentially a solution based on your modes. So instead of solving it in the physical coordinate system, it's solving it in the modal coordinate system. Well, this way is more efficient compared to the direct integration method. It's going to save you a lot of time. But the cons of these is highly depending on the engineering judgment of the mode that you're going to be taking to do this. So you want to make sure that you captured sufficient modes so that using this method can be accurate. And also you can vary the damping ratio for this. Now, I think a little bit side story here is nowadays since we all have computers, we have the luxury to just put in our load and then get the response. So when I was in a graduate school, I was in the University of Houston, and I was taking one of the dynamic courses from a professor named Andy Valesos, who's I think the pioneer and one of the most famous professors in the dynamics. And then he used to say a story about when he first became a professor. He was a young professor in the 50s and 60s, and one of his students, his whole PhD thesis, his whole thesis was to get a response for a seismic excitation. So basically doing a time history analysis by hand. So I guess nowadays it's much more convenient to do it using computer. Now, to sum up the first part of my presentation, so in a RISA, what we can perform is essentially we can do the ELF, the equivalent lateral force method. This is a linear static method. We can do this in RISA-3D, and we can also perform the RSA, which is a linear dynamic analysis. So for the time history analysis, we can do the linear dynamic. Time history analysis, you can do a linear or a nonlinear. But currently, RISA has a linear solver, so we're limited to do the linear dynamic analysis for the time history. That's pretty much conclude the first part of my presentation. In the second part, I would like to do a demo of 3 different models in RISA-3D. So I wanted to quickly talk about them now before I jump into them. So the first model, I wanted to do a Eigen solution to get a period of and a natural frequency of these 1-story building. So this story, I intentionally selected a L-shaped building to show you very common question that we receive in a support. Like, do I wanted to use a lumped mass to represent the diaphragm mass, or I wanted to use a distributed mass? Which means that I might use an area load to represent my seismic mass, or I wanted to apply a single load to represent it. So in this model, I'm going to show you how to make that judgment. The second model I want to show is a RSA model, which is for this platforming here. So it has a 3-story made of like a steel members, and I have some plate member to represent the floor, and I have some braces on the level 1. So I'm going to run a RSA for this model. The third model is a time history. So since the time history oftentimes takes a long time to run, so I wanted to kind of showcase a simplified model here. So this is just a 1 bay of a kind of a moment frame building. So I'm going to apply some seismic load to this building and get a response and show you how we can view the result. So now let me jump to my RISA-3D. So this is a first model I wanted to show. I think most of you hopefully have seen this new user interface for the V18 version. So for the V18 version, we did we did a really major change on the platform. So in the new V18, as you can see that UIs are completely different. These are based on a new Microsoft .NET platform. So the reason we are switching this to this new platform is because the old platform is very limited in terms of a lot of the features that our user asks us to add. And then, so this new platform gives us the opportunity to do a lot of different things. As you can see that we organize all these buttons based on the actual function. So we're trying to make it as logic as possible so that it will be easier for the user to find it. I know a lot of the users have been using our software for like maybe 15, 20 years, and they're so used to where the buttons are, because in a old V17 user interface, all the buttons on the same screen, and if you know where they are, it's very quick that you can collect it. But as I said, we reorganize the button based on the actual functions of it, and we like for us, we have been using the old version also for a long time, but as we are using the new version, we find like once you are used to where the buttons are, it's actually much better and much easier for you to find them compared to the old version. And also, as I mentioned, we have the different new features we wanted to make it possible for the user to have it. That's why we switch to this new platform. So I wanted to talk a little bit about some dynamic settings that I mentioned in my presentation here. Excuse me. So if you're in the model setting here and you click the advanced button over here, you can see that we have several different solvers for the dynamic: standard solver, accelerated solver, and risk vector solver. And for time history, we have the model superposition and direct integration. Here we can see that we have some parameters that we can define for the HHT method in here. Now, I'm sorry for that. And so for this particular model here, the reason I wanted to show this model is for showcase how do you decide if you use a lumped mass or distributed mass. Now, if I display the load here, we have a display load button here. So we have two different load combination. One is a lumped mass, which I calculate the total weight of this diaphragm here. And then I lump it all to this center of gravity here. And the second one is the gravity dead load, which I was using a distributed load. So the difference between this is if you use a single lumped mass, you only have one single mass in here. So you can see that you have only 3 degree of freedom system. So you can go X direction, Y direction, and Z direction. While if you're using a distributed load, the program will automatically consider the mass distributed to each of the node, and each of the node will have its own degree of freedom. So you will have a lot more modes you can capture. So in this case, we happen to have a torsional mode that's going to govern because of the arrow shape and the stiffness of the system. So if we run this analysis over here, we're going to select the dynamic eigensolution response spectra option. So we hit solve. So now first we're going to solve for the lumped mass. Since we have only 3 degree of freedom, we're going to only select 3 modes. So these options are for RSA. We're going to talk about that later on. So we can start the solution here. And here is our frequencies, period, and then the participation factors of each mode. As we can see that we have a governing period, governing mode 2 in X direction and governing mode 1 in Z direction. So we can actually check the mode shape. That will tell you more information of how the mode looks like. So as you can see that now we have, it's very convenient. We can stack the window if you wanted to keep it all in the same screen. We can click on this and drag. So we will have this little button here, which we can stack it on different location. We can put it on the right-hand side here. And now we can view our mode shape. So for viewing a result, we're going to go to the View tab here. And then we're going to click the Display the Result. So here we can see that we have a mode shape here. Now I'm going to check this to keep this window open. So we click Animate. As you can see that we can display the mode shape. In this case, it's pretty straightforward since you have only X and Z direction as degree of freedom. So this is your mode 1, and then your mode 2 will be something like this in the other direction. But now if we would run this analysis in a distributed mass again, so now I'm going to increase my mode. I'm going to use like 6 of them. And then I'm going to change it to gravity dead load, which is a distributed error load. So let's start the solution here again. As you can see that now the mode is a little bit different than the previous one. As you can see in the X direction, we have actually 2 modes, mode shape 1 and 3, which have pretty much like the same or like very similar participation factor, meaning that there's no dominant mode if you're using the distributed mass. Now we can do the same thing and review your mode shaping here. So let's go to our view and the results. And then let's say how the mode shape 1 looks like. As you can see here that our mode shape is a torsional mode for the mode shape 1. So this mode shape was not possible to capture if you use a lumped mass because that doesn't have the rotational mass linked to it. It can only move like in a single direction. And if we're checking the mode shape 2, this is a mode that's pretty similar to previous. It's just it's just a lateral movement. And if we display mode shape 3, we can see that it's also another torsional mode. So these examples give you a very good case that, as an engineer, you need to make decisions based on the building. If you have a relatively regular building layout, there's no like a horizontal irregularity or vertical irregularity, you can go ahead and use a lumped mass. It'll save you tons of time in solution. But if you have a case like this, you may want to consider using a distributed mass for doing the Eigen solution. Now, this pretty much sum up the first model. Now, let me go to the second model, which is RSA. So for the RSA result, we can see that we have this platform, 3 levels, pretty straightforward. Now, before we jump to the RSA, I want to show you here in the Advanced tab, we have some buttons over here which you can check different stuff. These are more advanced things. That's why we put it in this tab. So here, there is a response spectral buttons. Here you can see that we have a whole library of different spectrum and different codes. So you can click to view it, and then it shows the information of how this graph is developed based on different code. Now we give the user the freedom to create their own spectrum if they want. You can click this one, the generate, and then directly input the spectrum you wanted to use if none of this code spectrum is intended. Now, for doing a RSA, you have to define your RSA load in this model. So here, going back to the Home tab, if we click the Load Combination button over here, I have some pre-selected or predefined RSA load in here, the SX, SD. The SX stands for the RSA load in the X direction, and SD is the same story. So if you wanted to create these load combination from scratch, you can click here the load combination generator. When you click it, this generator is essentially to help you to generate some code standard load combination. So here you can see that you can select different codes in here. And we have the gravity load combination, wind load combination, and seismic load combination. So in this case, we're going to do the seismic load combination. We have 2 different seismic load combination generator, the regular one and the overstrength one, because some of the code require you to perform a overstrength load combination to check the member strengths, like particular member strengths, let's say. So in this case, we're going to only use the X and Z in the RSA. So if you check this one, and then you can do the reverse and include other factors. But here we're going to keep it simple just to use the X and Z in the RSA. Now, if you hit the generate button, as you can see, there are some new RSA load combination are generated. So after you generate the load combination, as I mentioned in my presentation, the response from the RSA, from the spectrum, is based on a single degree of freedom system, which is elastic. So if you want to get actually your design force, you need to bring it back down to consider the ductility of the system. So you need to basically divide it by the R factor and times your IE. So this factor is called, in RISA, we call it scaling factor in here. So as you can see that in this predefined, I have the SX times SF, which stands for scaling factor. So you need to use this factor to times your response forces directly from the spectrum. So we have a way to define this scaling factor. You can click this button over here. This is a window that's basically telling you what your scaling factor is. So in this case, we have the base share multiplier. This multiplier is actually for a threshold we're going to talk about later on for ELF. So I'm going to talk about this one later. And we have the static base share. This static base share is actually from your ELF method, from your equivalent lateral force method. And then we have the unscaled base share. This base share is calculated directly from the RSA, so it's unscaled. So for this case, to get the most updated scaling factor, we need to do a calculation based on ELF method. So this window is basically to calculate that. So you can select your seismic mass. Here I already defined a load combination, which is for seismic mass. I'm going to select it and click calculate the load. So this step, basically, it is doing the ELF method to get a dominant frequency period, plug into the curve, get your response, and calculate your base share. So And then when I hit OK, you see that these forces are updated. Now we can do a RSA result. So let's do an RSA result here. Here I selected the 10 modes, and I'll also select the same seismic mass over here. And as you can see that in the RSA window, we have multiple options you can select. We can select different method for the combination. Here I was using CQC, and you can change your damping ratios and cutoff frequencies. And then you can select if you wanted to consider the residual mass or not. So a lot of these options, I don't have time to talk about them in detail today, but if you go to our online help file at RISA.com, we have explanations of how to select all these values to get a more accurate result depending on your structure. So here I'm gonna do it for X direction and Z direction because those are the two major lateral directions of my structure. And for the code spectrum, I'm gonna select the most recent ASC 7 2016 version. So here you can see that we have another checkbox here called the use the dominant mode for signage. So this one I want to talk about it because it's very, very important. So when using your combination of different modes, as I mentioned in the my slides, if you're using any one of these modes, so you have a square root of the squares, sum of the squares inside your equation. So when doing square root and squares, and then you lose your sign, you lose your signage for all the forces or like your joint reactions or your displacement. So at the very end, you might end up with some very weird reactions at the node or some weird deflection shape. So that's because when doing the combination, you lost all the signage. So here we provided an option of using the dominant mode shape for the signage, basically meaning that, okay, so all the joint reaction displacement, I'm gonna use the signage depending on the governing mode shape, regardless of what are the rest of the mode shape. So most of the cases, your total joint reaction or like base shear will be mostly determined by these dominant mode shapes. So by checking this box, I would say 90% of the cases you're gonna get the correct signage for your RSA result. So this box is recommended to check all the time. So now we can start the solution. And then as we can see that these unskilled base shear was updated as well. So now we can hit the update button over here. So by doing that, we are recalculating this factor, this scaling factor. So as you can see that we have two different limits. The limit number one is a I over R limit. So this is essentially calculating what's your I over R value. So this value will be used to times the RSA response to get one of the forces. And then the other limit that the ASC 7 required is once you get your RSA design force, it cannot be lower than your equivalent lateral force method force. Meaning that if, for instance, using the RSA, I've got maybe, in this case, 233 times whatever the R is. If the force is smaller than my ELF method, then I have to use bring it up to the ELF method to use this. So in RISA, we are comparing these two factor, and then we are using the larger one of these two to get your scaling factor. So this 0.85 factor here is essentially ASC 710 code. I think in the 710 code, the code allowed you to use 85% of the ELF method, and this multiplier is to consider that. But in the new code, which is ASC 716, this percentage has been changed to 100%. So this value will be changed to 1.0 if you're using the most recent ASC 7 code. So by doing that, we are finishing calculating our scaling factor. So if you wanted to apply your scaling factor into all of the RSA load combination, you can check this box and then hit OK. I think I forgot to mention that for the scale factor, instead of using the code like automatic calculating, using the program, you can also select the user input and input your own scaling factor if needed. So now I'm going to check this box to apply all the scaling factor to my RSA load combination. So when I hit OK, we can see that the scaling factor was applied to all of them. So now I'm going to delete all these load combinations that I created and use the predefined one. So now I'm going to go ahead and run my RSA analysis. So if I hit run batch plus envelope, it requires me to run the Eigen solution first to get all the mode shape. So here, let's redo this again. Now we get all our period and all the mode shapes. And then we can run again. It runs pretty quick. And now we have finished our RSA result. So the first thing I always wanted to do after I run an analysis is to check the deflection of it. As you can see that we can change different load combination to check the deflection of the structure under different RSA, just to make sure that the load direction is as expected. The second thing we can check is probably the member code check. So we have here this code check spreadsheet. Once you hit this spreadsheet, you can see that we listed all the code checks in here for different members. And in this case, I have a lot of hot roll members in here listed. So we can actually click this code check, which is a unity check ratio, or some engineers call it a DCR. And we can right click this and use a sort and a sort from maximum to minimum. And then we can just, highlight what are the members that has a largest UC. So in this case, it seems like we have some like single angle that are overstressed. These single angles are the braces in the level 1. So we can, right click these in the spreadsheet and check the detail report of this particular member. So this is very convenient. As you can see that in the new V18 version, we did a really, really big change for the detail report. And here in this new detail report, we are providing a lot more information compared to the previous version. So we have some general member information over here, and we have all the force diagrams, axial load, shear, and torsion, and then moment listed in here. And in the code check, we have a lot of different tabs in here. And in the previous version, we only reported you the final result, but in this V18 version, now we are actually showing you every single step for the calculation for capacity and also for the demand side. So you can review them rather easily. And we added this description of what each parameter is and add the code references, if any. So this one, if you wanted to just print it, it can be used as a very good calculation report or like a calculation package for the reviewers to perform a review. Now, as you can see that we listed here, this member is filled by combined bending and axial load. We have UC equal to 1.7. We probably wanted to increase the size of the member to help it a little bit. And if you wanted to let the program to do the design for you, we do have a suggested design spreadsheet. As you can see that we will design the shape automatically and provide you this suggested shape. So you can rerun and solve the model if you wanted to use this shape. Or if you want to change it by yourself, you can do that as well. So these pretty much sum up the response spectrum model. So I'm going to go and I'm going to go to the last model I'm going to show today, which is a time history model here. So in this model, it's actually a bay of a moment frame. I'm going to put it in the X and Y plane. So it has a moment frame, and it's like a multiple levels. And then I wanted to show you the time history. It's in the advanced tab as well. We have a time history button over here. So once you hit that, you can see that we have a whole library of the regularly used time history excitations here. So if you wanted to review them, you can click the View button here. So this one is not easy to say because it's the period is so small. I think I'm going to show you another one for seismic. For instance, this is a Northridge earthquake we're going to be using today. So once you click the view, you can see that this is your response, and you can basically click on different points and then check the result of it. Our steps and then the excitations are listed in here in the spreadsheet, and then the total duration is listed in here as well. So this will help you kind of review the seismic excitations you've had imported, and then you can generate your own time history functions in here depending on your need, or you can use our import. You can use our import functions here, and then you can create a TXT file and then import it directly. So for the TXT file, we do have some format requirements for how the program can load it. So those information can also be found on our online help file. If you go to RISA.com and go to our online help and search time history, all those information should be there listed if you wanted to check that. So for applying time history load, similar as the RSA, we need to define our load combinations over here. So here I have two load combinations. One is a basic load combination, which is a dead load. That's to just define my seismic mass. And the other one is a time history load combination. So here I have a T1, which is a time history, which stands for a time history load. So as you can see here, we have a time history load 2. So in order to check in detail how to define this time history load, we have a time history load spreadsheet. So if you click here, you can see that we have a time history tag and the label of it. And then you can define your different time step over here. Here we're using 0.01 seconds. And you can define what type of excitations you wanted to use for this particular function. You can either select it as an acceleration or force. So here, the seismic excitations, I'm going to choose a Northridge. And then here, this triple dot button will also direct you to the time history function library as well. So it's very convenient for you to review it while you want to define your time history. And then the nodes here basically define what load you want, like this load, which node you want to apply to your structure. So in this case, since it's a seismic excitation, it'll be applied to every single node of the system. So if you would have run the, for instance, a blast analysis, which you will be applying to certain nodes, or if you're doing a equipment vibration analysis, it might be attached to a single node. So here you needed to define the node number here so that the load will be only applied to those particular node or nodes. And here you need to define also the direction where you wanted to apply these loads to. So you can apply it in X direction, Y direction, or assign it in the as a moment in a rotational direction. And these are some other factors. Today I won't have time to talk about all of them in detail. As always, you can find those informations in our help documents. I think I forgot to mention that if you are in the particular window in RISA-3D, you can just hit F1. It'll actually go to the particular help file. Let's talk about all this. So if you're actually using the software, it's very convenient to do that. So previously, the help file was in the, we installed it locally, and then it'll pop up as a window. But now we actually changed it into a web page version, web page format. So it's more convenient for the user to use. Now, after defining our time history analysis, we're ready to run the analysis. So if we hit here, run the solution, as you can see that it also requires you to run the dynamic analysis, the Eigen solution, before you do the time history. So I think as I mentioned in the presentation, we're using direct integration method. So theoretically, we don't actually need to run the eigen solution. But we are now still require the user to do that is because we wanted to use the opportunity of running a eigen solution to assemble your mass matrix and stiffness matrix so that we make sure the system is ready to go before we jump into a more complicated time history analysis. That's basically what this step is for. So now we are running the eigen solution again. So I'm gonna start solution. So we get all our mode shapes and the participation factors in here. Now we're gonna run the time history analysis. As you can see here, we have 5,000 different steps in here. So it will take actually quite a while to run this. What I did to save some time in here is I already ran a model similar, same model as this one, and I already saved the result. So we can open that up and show you quickly the result display instead of waiting here for like maybe 5 minutes. So now let me open it up, that model here. So it's essentially the same model, but I have the result already saved. So I'm going to go to the X and Y view here. So for displaying the results, again, we will go to the View tab. In the View tab, this is where you want to view all the stuff. For instance, before you run analysis, we have the model view, which you can turn on and off for different stuff, like the model label, and then you can do a render view. You can change your percentage you want it to show for different members. And after you run analysis, we always wanted to click the result display button to show the result. So once you hit that, you can see that we have a new time history result display button. So we're gonna click that, and then we're gonna hit the keep this window open, so we don't need to re-click that button. And then we're gonna click animate button here to generate a response in an animation. So once we click that, you can see that there's a new window pop out. I'm gonna stack this window at the very center. And now I'm gonna go to the XY view over here. And now, as you can see that there's no actual movement. That's because it's still in the first few steps in the excitation. So one of the ways to check where you are in relative to your excitation is to use a trace button. So the trace button is essentially created so that you can trace the response of a particular node. So you know how big the displacement is. So in this case, I'm gonna do it for 42, node 42, which is the node over here on the left top corner. So when I hit OK, you can see that we have the response listed in here. The response is between, I think, 2 inches positive or maximum, positive or negative in here. So as you can see here, we're still in the early stage where there's not much load applied. So to save us some time, we can go ahead and pause here. And then we can go to the probably, let's see, 20 seconds. We can type in 20 here and then hit the play button. So you can see that in these steps, we have some displacement in here. So we can increase animation speed here by slide this bar to just make it go faster. And then we can change the scale of the displacement to make it more obvious. So let's slide the slider here to 128 times the actual deflection. As you can see that it's a little bit exaggerated, but it helps you to check what, like how your deformation shape is. So as you can see here that our response is irrelevant to time. So after you perform this time history analysis, what the program is going to do is to take the largest internal forces to use as your code check for every single member for each step. So if you click the code check button over here, as you can see that we listed all the members code check. So similar thing, you can do a sorting of the result from maximum to minimum. And here you can see that our members are doing a pretty good job. The maximum UC is only 0.31. So as you can see that for the load combination, this basically tells you what's the governing steps for your time history analysis. In this case, we can see that it's a step 2,775. So you can go to your steps in this animation to make sure that, oh, I'm having actually the very large deformation for my member at this step to make sure the program is doing the correct thing. So here we can also right click and go to our detail report to check your result in here. So this result will be showing you as an envelope for the governing step in your time history analysis. So similar thing for suggested design, as you can see that since your UC is way below 1, so the program will automatically assign some lighter section for your design. So if you want to choose it, you can just right click and do the redesign using those sections. So with that, that pretty much concluded my presentation here today. And as always, if you have any questions for this presentation, or if you have any questions for in general for RISA, you can always contact our RISA support at RISA.com. I think in RISA.com, if you go to the support button over here, it'll lead you to this contact information of our tech support. So you can either send an email to us to support@RISA.com, or you can call us. So for model-specific questions, we prefer to the customer to send us emails because you can attach the model in it, and then you can describe your issue in there, and we should be able to send you back our response within a couple of hours typically. And we can send you screenshots and stuff like that. So oftentimes that's easier for communication. Or you can call us for any general questions. For instance, I don't know how to do certain things in RISA, or like I'm seeing some weird behavior, stuff like that. So we will be able to help you on those general questions through the phone calls. So our tech support is 6 a.m. from 6 a.m. to 5 p.m. Pacific time. So you can call us between Monday and Friday. So yes, at last I want to thank you all for your attention for today's webinar, and have a great rest of your day.